Welcome to section 3 of chapter 22, and we're going to talk about functional groups. So our only main idea for this section is that functional groups can classify organic compounds. So we will investigate and understand how basic chemical properties relate to organic chemistry and biochemistry. Some of the key concepts will include uses in pharmaceuticals and genetics, petrochemicals and plastics and food. So just looking at the key terms, something that might be familiar to you is amines, and amines are compounds that contain a nitrogen atom with a lone pair. So for example, NH2 would be an amine, or NH3 would be an amine. So anything with a nitrogen atom. And then a carboxylic acid is usually this compound. But we will go over all of them in more detail. So functional groups can classify organic compounds. And a functional group is defined as an atom or group of atoms that is responsible for the specific properties of an organic compound. So functional groups are all about classifying compounds by the properties. A functional group undergoes the same types of chemical reactions in every molecule in which it is found. Therefore, compounds with similar groups are classified together. The compounds in figure 3.1 have 4 carbon atoms, but they have very different physical properties due to their different functional groups. Some functional groups and their characteristic general formulas are shown in figure 3.2. Many of the names may be familiar to you. In figure 3.1, it's quite easy to observe that even if the number of carbon atoms in the compounds is the same, but functional groups are different, the properties will be very different. So it's the functional groups that make the difference in the properties of a compound. Because as we see in figure 3.1, all 5 of these compounds have 4 carbon atoms, so the number of carbon atoms does not change, but it's the functional groups that change. The first one is butane. It must be familiar to all of us as we looked at it in sections 1 and 2. And the structural formula, we also saw it before. And then we have these 3 properties for each of the compounds: melting point, boiling point, and density. The next one is 1-butanol. We have this hydroxide functional group instead of a hydrogen atom compared to butane. Then butanoic acid, it's a butanoic acid because there's a hydroxylic acid functional group instead of a hydroxide or hydrogen group as in the latter two. And then 2-butanone, here we have a carbonyl group. And then diethyl ether, which we will look at more closely a little bit later. And then figure 3.2 introduces us to the classes of organic compounds and how exactly they're called. So we have alcohol, and then its functional group is the hydroxide group, OH, and the general formula is R, and R stands for the rest of the molecule. So this is like the rest of the molecule, and the molecule will have a hydroxide group attached to the end. Then alkyl halide will have a molecule, and then one of the halogens will be attached to the end. So X stands for one of the halogens. And then ether means there will be an oxygen atom in the middle of the compound. Then aldehyde is a carbonyl group, then a hydrogen on the other side with the rest of the molecule. on the other side. So ketone, a carbonyl group in the middle of the organic compound, and then amine is just a nitrogen atom connected to other atoms. And then carboxylic acid is the COOH. And then ester is a carbonyl group and an oxygen attached to the rest of the molecule. It'll also be found in the middle of the molecule. And now there's this check for understanding question. We have to compare aldehyde and a ketone and find the difference between them. So feel free to pause and think about it for a second, and we're going to go over the answer. Okay, so here we have aldehyde and ketone. As I said, aldehyde is found at the end of a molecule of a carbon chain. That is why it has a hydrogen atom on the side to make up for not being in the middle. But a ketone is found within a carbon chain. So this is a continuation of the organic compound as well as this. So a ketone is sandwiched between the two parts of a carbon chain. But an aldehyde is found at the end of the chain. And now we will zoom in on each of the functional groups. So first is alcohol. Alcohols are organic compounds that contain one or more hydroxyl groups. So the defining feature of an alcohol is a hydroxyl group, an OH group. The general formula for a class of organic compounds consists of the functional group, OH in this case, and the letter R, which stands for the rest of the molecule. The general formula for alcohols is R bonded to OH. Customarily, alcohols get their names by appending the suffix OL to the hydrocarbon. For example, butane becomes butanol. Hydrogen bonding in alcohols explains some of their properties and uses. So we're told that alcohols have hydrogen bonds. Cold creams, lipsticks, body lotions, and similar products generally include the alcohol 1,2,3-propanethiol, commonly called glycerol, to keep them moist. A model for glycerol is shown in figure 3.3. Multiple hydroxyl groups allow glycerol to form many hydrogen bonds with water molecules. So 1,2,3-propanethiol has a common name, glycerol. And looking at figure 3.3, we know that glycerol contains 3 hydroxyl groups. This structure allows it to form multiple hydrogen bonds with water. Glycerol is added to skin products as a moisturizer. Now let's decode this name, 1,2,3-propanethiol. It's commonly called glycerol, but we also have this 3D structural model. So from the prefix of prop, we know that the compound will have 3 carbon atoms. We can also see that because there are 3 green atoms here, and green represents carbon. And then, so it's an alkane, meaning there will be only single bonds and enough hydrogens to make each carbon atom happy. Actually, let's not do this at this point. For now, let's jump to the other part, triol. We know that the suffix OL means that it's an alcohol, so there will be hydroxide groups, and tri means that there will be 3 of them. So we'll have 3 hydroxide groups, OH, OH. And 1, 2, 3 simply means that they are found on the first, second, and third carbon atom. And now we can add the rest of the hydrogen atoms to make all carbon atoms happy. So here we have our structural formula for glycerol, or 1,2,3-propane-triol. Alcohols are sometimes used today as alternative fuels and as octane enhancers in fuel for automobiles. Ethanol is combined with gasoline, for example, in a 1:9 ratio to produce gasohol. Gasohol sounds a little funny. So ethanol, not to be confused with ethane, which is now familiar to us. Ethanol. Let's draw its structural formula. So eth means there are 2 carbon atoms. It's an alcohol because it has an OL ending, meaning it has, so there's no prefix, Greek prefix to indicate the number of hydroxide groups, which means that there's only one. So we'll have one hydroxide group, and the rest is simply hydrogen atoms with single bonds. Here we have the structural formula for ethanol. Some experts have promoted the use of gasohol as fuel for automobiles because it burns more cleanly and efficiently. However, there are also disadvantages. The combustion of ethanol produces only about 60% as much energy per gram as the combustion of gasoline does. So ethanol is not as efficient as gasoline by itself. And so when we mix the two, the efficiency will be in between ethanols and gasolines. The presence of ethanol also causes increased water absorption in the fuel. Our second class of functional groups is alkyl halides. They are organic compounds in which one or more halogen atoms, fluorine, chlorine, bromine, or iodine, are substituted for one or more hydrogen atoms in a hydrocarbon. So you see an alkyl halide if you have a carbon atom, and instead of the hydrogen atoms that we're used to seeing, we'll have halogen atoms. Thus the name, halides. So the alkyl part comes from the fact that they're kind of alkyl groups because they're attached to the parent carbon atom. So that's where the name alkyl comes from. And then halides is from the fact that we have halogen alkyl groups. So halides for halogens. Because -X is often used to represent any halogen, an alkyl halide may be represented by the general formula R bonded to an X. Alkyl halides are some of the most widely used organic chemicals. A family of alkyl halides that has received widespread attention in recent years is the chlorofluorocarbons, or abbreviated CFCs. CFCs are alkyl halides that contain both chlorine and fluorine. The formulas for 2 widely used CFCs, Freon 11 and Freon 12, are shown below. So just to make it a little clear, we'll jump to the next sentence here. It says CFCs, which have been used as liquid refrigerants. So we're talking about liquid refrigerants, and that is why these organic chemicals are widely used. And then if you're wondering where the name Freon came from, it's the name of the trademark that produces these chlorofluorocarbons. And so here we have trichlorofluoromethane. A common name is Freon 11. But if we break this long name down, we have methane, meaning it's an alkane with single bonds, and then it has a single carbon atom. That's why we have meth. And then trichloro, because we have 3 chlorine atoms and 1 fluorine atom, so it's just fluoro. And our second one is dichloro-difluoromethane, because we have 2 chlorine atoms, 2 fluorine atoms, and it's still a single carbon atom, and it's still an alkene with single bonds. So CFCs, which have been used as liquid refrigerants, contribute to the destruction of ozone in the upper atmosphere. When released into the atmosphere, CFCs can break down and release free chlorine atoms. So when released into the atmosphere, these chlorofluorocarbons, in this case here we have this compound, dichloro-difluoromethane. When released into the atmosphere, it can break down under the influence of solar radiation into a single chlorine atom, and then this compound, which is chloro-difluoromethane. So the released chlorine atoms attacks molecules of ozone, O3, found in the upper atmosphere. So this single chlorine atom will harm our ozone layer, which protects us from the sun's harmful effects. And then the ozone is converted to diatomic oxygen. So this is the first chemical reaction that will happen, and this is the next one. So when chlorine reaches the ozone layer, the result is diatomic oxygen and chloroxide. Chlorine atoms are then eventually regenerated in various ways, including the reaction of chloroxide with oxygen. So when chloroxide reacts with oxygen, the products are chlorine and diatomic oxygen. So this makes it possible for a single chlorine atom to destroy thousands of ozone molecules. And this happens because when chlorofluorocarbon first decomposes into a chlorine atom and chloro-difluoromethane, this one chlorine atom will start harming the ozone layer. So here it will react with the ozone layer. This is the same chlorine atom as here. And the products that will be formed are a chloroxide molecule and a diatomic oxygen. Then the chlorine atom is now a part of this molecule, but it will reform back into monoatomic chlorine in this reaction. And then this single chlorine atom will be able to harm the ozone layer again and again with these two reactions, this reaction over here and this one, constantly contributing to the chlorine atom go back to its original monoatomic state again and again, and harming that ozone layer. And because CFCs are a major cause of ozone depletion, more than 100 nations signed an agreement in 1987 to reduce the amount of CFCs produced. Another alkyl halide is tetrafluoroethene, C2F4. Let's try and draw the structural formula for tetrafluoroethene. First off, we see the ending -ene, so it's an alkene. So we're looking at a compound with at least one double bond. Then tetrafluoro indicates that there are 4 fluorine atoms, and F means there are 2, and we can also see that from the molecular formula. So we'll have 2 carbon atoms, and since fluorine atoms need only 1 extra electron to be happy, they will need to be connected by single bonds, 2 for each carbon, meaning that the 2 carbons will have a double bond. So it is joined in long chains to make a material with the trade name Teflon. Because of the unreactive carbon-fluorine bond, Teflon is inactive and stable to about 325 degrees Celsius. So now we also know that the carbon-fluorine bond is unreactive. It also has a low coefficient of friction, which means that other objects slide smoothly over its surface. These properties enable Teflon to be used in heat-resistant machine parts that cannot be lubricated. It is also used in making utensils with non-stick surfaces, such as the frying pan in figure 3.4. The non-stick coating on this pan is made of Teflon and alkyl halide. It has made our life much easier. Ethers are organic compounds in which two hydrocarbon groups are bonded to the same atom of oxygen. They can be represented by the general formula R bonded to an oxygen atom bonded to R prime. This formula R prime may be the same hydrocarbon group as R or a different one. So it just means that this is like the rest of the organic compound, and we have an oxygen atom in between. Like alkenes, ethers are not very reactive compounds, so they are commonly used as solvents. And we'll talk about the rest of the functional groups in the next video.